welcome all you guys here today. It's great to have you, Chris. This is kind of an introduction to embodied carbon. Again, Maurice, you've already come to the advanced, but hopefully this is still helpful. Chris is just a wealth of knowledge on the topic, and so we'll keep things pretty informal. There are only going to be probably 8 or 9 folks joining online, and then we'll see if some other folks trickle in. But we want this to be as helpful to you folks as possible. Chris is really adaptable, so if you want to jump in, please do. If you're really worried about something that has been said or you're questioning it, just jump in. I wanted to thank FortisBC. They're the funders of this workshop series. And again, if you have any questions through it, just jump in. But for now, we'll pass things over to Chris and he'll present on the topic.
Okay, great. Thanks everybody for joining today. It's been a real pleasure to work with Natalie and the City of Nelson and FortisBC on both the study that went ahead of this series of workshops and these workshops too. It's really encouraging to see the sort of interest in embodied carbon coming from your region, and there's some work going on with a larger group of small municipalities in BC as well as in Vancouver. So really BC is at the forefront of thinking about this topic and hopefully acting on it too. So I'm really glad to be able to be part of all of that. So what I'm hoping is that by the end of this this presentation, you're kind of feeling confident that you know what these embodied carbon emissions are, how we calculate them, and why it's important to be tackling this. And like Natalie said, I'm totally open to just having you jump in and ask questions as we go. If there's anything that you're sort of unclear about or want to sort of get a bit deeper into, we can definitely do that. So I like to start these presentations by kind of giving us all a pat on the back, because over the last 20 years, we've made a huge dent in the operating emissions of buildings, both from sort of the voluntary side, the private sector getting serious about it, through third-party things like Passive House and the various net zero programs that exist, and then also through our codes and code enforcement. Everybody has kind of really stepped up the game over the last, especially decade, and really started to reduce the operating emissions side of buildings. So, we've done this great job of paying attention to that, and that sort of, especially with the BC step code, we can sort of see the point where, it really might be possible to get our housing stock down to zero or very close to zero on the operating emission side. But what we haven't really spent much time thinking about until quite recently is, what are the emissions associated with getting these buildings built in the first place? And also, you can have in the back of your mind the same question exists for how we're going to renovate all the buildings that we need to do to also get them on a net zero operational pathway. Whether it's renovations or new construction, all this industrial activity happens to make all these materials. So making building materials is the single biggest share of the flows of materials in North America. About 75% of the mass of everything that gets made and moved around goes into buildings. So it's pretty substantial. And so for this presentation, we're kind of turning our eye to that side of the equation. A little bit about myself. I come from a background as a design builder, and more recently over the last couple of years as a researcher. And the start of my dive into this topic of embodied carbon came with trying to answer in 2012, what is the carbon footprint of the materials for one of the projects we were doing, the one that's shown here. Because we knew that we were doing a really great job of getting that house down to zero in terms of its operating emissions. We knew that we were doing a really great job in terms of eliminating completely any sort of toxicity concerns with materials in the building. But we didn't know what the actual carbon footprint of that house was. And it turned out in 2012 that this was actually a really difficult question to answer. There hadn't been much attention focused in this area yet. And so as I sort of set out to uncover the answer for our own practice, it turns out that other people were starting to think about that then, and I ended up being part of a sort of group of researchers who over the last 10 years have really tried to bring some attention and some clarity to all of this. So in 2016, I went back to school and did a master's degree, and the results of that kind of kicked off Builders for Climate Action and all of the work that's happened since. So just to sort of give you a sense of what we need to look at if we want to figure out the carbon footprint of the materials in a building and therefore of the building itself, we have to think about the whole life cycle of that building. So you can sort of see in life cycle assessment the phases of a building's lifespan are kind of categorized in life cycle assessment. Everything from the extraction of raw materials at the very beginning of the product's life to eventual disposal at the end of life, whether that's landfilling or incineration or recycling. And there are sort of emissions attributed to all of those different phases. There are different sort of lenses that people put to this kind of study, the most common of which is called a cradle to gate analysis. So it's really just looking at those first three phases, which is kind of getting a product made. So getting the raw materials wherever they come from, getting those materials to a factory and turning those raw materials into the product that's going to go into the building. All of that is kind of captured in a cradle to gate analysis. You'll also sometimes see people analyzing what's called upfront embodied carbon. So that's the product phase plus getting the materials to a site, plus whatever emissions happen in the actual construction process. And then sometimes you'll see a whole life cycle approach where you're actually adding up the emissions at every phase from start to finish. What I'm going to talk to you about today is entirely focused just on the product phase. In life cycle assessment, these first three phases are called A1, A2, and A3. So these A phase emissions, the reason that I'm focused on those is because, as you can see, they are the largest share of emissions from building materials. Depending on the material, it sort of ranges from about 65 to 80% of all the emissions over the whole lifespan are going to happen there. So that's one reason to concentrate on them. The other reason to concentrate on them is that this is the largest data set we have, and it's also the most accurate data set we have, because it's really quite straightforward to go to or to analyze the activities of a given manufacturer and get a really strong sense of what these product emissions are. As you move along the life cycle, the numbers kind of get fuzzier, right? We don't always know how far it was transported to a site or by what type of transportation. We know less about what actually goes on the site. We don't know very much about when those materials get changed or what's involved in maintaining them. And then, we're also sort of guessing at what happens at the end of the life. So because we know the upfront numbers and we know they're really big, that's where everything that I'm going to show you today is focused just on those three product phases. We know what those product phase emissions are from these documents called EPDs, Environmental Product Declarations. And this was an ISO methodology that emerged about a decade ago as a way to kind of standardize how you do this. So prior to that, you would have people performing these life cycle assessments on different products, but they'd be considering different things along the life cycle in different ways, counting some things, not counting other things. And so what the EPD does is say, well, for a given category of materials, here's what you count, here's how you count it, here's the data that's acceptable, here's data that's not acceptable. And so it kind of gives us the closest thing that we can get to a sort of apples to apples comparison between products that do the same thing in a building.
And sorry, Chris, that was for cradle to gate?
Well,
Like
you
the first
can,
3 phases?
sorry, EPDs can cover from like can do a sort of cradle to grave analysis, but most typically they do cradle to gate. So when I say that there's the biggest data set for cradle to gate, it's because if you look at 100 EPDs, probably about 60% of them only do cradle to gate, and how they do the other parts. That ISO methodology, it's great to have a methodology, but it introduces a lot of vagaries into the numbers. So in other words, you sort of take national averages for what happens to materials at the end of their life, and national averages for what gets incinerated, what goes to landfill, what emissions come out of those landfills, and so it gets a bit fuzzier, even though the rules are consistent. Whereas the rules and the reporting for A1 to A3 are pretty solid. So in those EPDs, the results are shown as this. It's CO2e, so carbon dioxide equivalent. And the reason for that is it's sort of a common denominator for all the greenhouse gases that might be emitted along the path of that material being created. So if we looked at each of the greenhouse gases separately, you'd get this sort of strange answer where material A might have this much CO2, this much methane, this much CFCs, whatever the chemicals happen to be, all of which impact the climate differently. And so it would be hard to look at two materials across 7 different greenhouse gases, all with different amounts. So CO2e takes the climate impact of all the gases that are emitted in making the product and sort of turns it into this carbon dioxide equivalent. So, methane, I don't remember the exact number, but a kilogram of methane has the same impact in the atmosphere as 30 odd kilograms of carbon dioxide. So we sort of put it all under this this common denominator of carbon dioxide equivalent, so that it's easier to compare across different profiles of greenhouse gases that might come from different products. And so if you wade into some EPDs, what you find when you finally find the results section in the document is a number that's of kilograms of carbon dioxide equivalent per a certain unit of material. So I'm showing you 3 different industry average EPD results here. So one for North American softwood, and you can see it's 42-ish kilograms of CO2e per cubic meter of wood. Concrete, the average in Canada is 304 kilograms per cubic meter of concrete, and steel, the average is 1.16 tons of CO2e per ton of steel. So those are great numbers, but if I'm trying to decide, well, do I use a wood post, a concrete post, or a steel post in my basement to hold up the beam, until you know how much of the material you're using, these numbers sort of don't mean anything. So from the EPD, we get this sort of factor, and then you have to apply that factor to your calculations for your building. So as I was trying to figure that out for every single material in our initial case study building, what I realized was, I need to build myself out a spreadsheet tool so I can calculate amounts of material that I need, so that I can multiply it by these EPD factors and get to an actual amount of emissions for that particular material in that building. And so that methodology became the sort of foundation of the BEAM tool that we have since developed and released as a free tool, so that anybody could use our formulas for material takeoffs and our database of EPD factors and start to see some different results. So if you do that set of calculations, now for my one post in the basement of the house, I'm just choosing that as an easy example, but a 6x6 post that's 8 feet long, and a 6-inch diameter concrete post, and a 3.5-inch diameter metal post, all of which would be reasonable options for holding up that beam in the basement. Now I can see what the actual carbon footprint of that material is in that application. And you can see that, you know, a single wood 6x6 has 4 kilograms of emissions, a 6-inch diameter concrete post has 12, and the hollow 3.5-inch diameter post would have 73. Now, you don't necessarily need to choose the lowest one, but now this becomes the kind of information where you can start making your decisions partly based on the carbon footprint of those materials. So if you go into the beam tool, what it does is it breaks the building up into all its different assemblies, and within those assemblies, the sort of types of materials that you would use. And so this is just a snapshot of a portion of the cavity insulation section in beam. So what you're seeing here is that for 100 square meters of wall area at an R value of 20 in this red box, these are the emissions results for a whole bunch of different materials, from, you know, aerogel through spray foam of different types to sheep's wool to mineral batt. And, you know, beam has about 4 more pages of different cavity insulations, but you can start to see when you look at these numbers that there's a pretty sizable difference between, you know, various options, all of which could feasibly be substituted for one another. So, you know, whether it's making a choice between a type of spray foam, or between, you know, type of batt insulation, or switching, you know, how you might approach the insulation of the building, you now have these numbers to give you some guidance. And so in addition to then looking at it one material at a time, you can use the tool to start to build out different assemblies and sort of looking at how different ways of building might compare. So, you know, here in assembly 1, this is a typical kind of like light wood frame wall with OSB sheathing and mineral wool batt and some EPS foam as the continuous insulation. And we're comparing that to an EPS foam insulated concrete form wall, and then to a structural insulated panel. So an OSB and EPS foam sandwich. And you can see, you know, the differences are quite apparent when you look at it at the assembly level. I can put together that frame wall at 100 square meters for 1,500 kilograms. But if I do that exact same wall that's achieving the same thermal performance, it's, you know, 3 times higher in carbon footprint, and the SIP wall sort of falls in between those two. So, you know, this becomes some information that you can use to sort of think about how you approach not just the material choice, but the assembly choices for a building. And then I know the numbers and text here is too small to see, but the tool can also be used to model out entire buildings. So you just sort of build up all the assemblies from ground up, and you can kind of see up at the top here in the red boxes, you know, the exact same building. So this is the same building model, but at the same performance level, but with different materials. This version of it has 81,000 kilograms of emissions, and this version has 20,000. So we've, you know, reduced the carbon footprint of this building by 75% by making a bunch of different material choices. So one of the things to sort of keep in mind when you're seeing these numbers that we're presenting and or using the beam tool is that we're not accounting for everything that goes into the house. We are accounting for the structure, enclosure, and partitions. And that's for a few reasons. This is where the biggest data set is. We have really good information, multiple data points on most of these material options. The materials last for a long time in the building, and it's the place where a user, either a builder or designer, can make some pretty substantial impacts on the overall carbon footprint of the building by knowing these numbers. On the other side, the things that we're not counting, the biggest one right now would be the sort of all the mechanical, electrical, and plumbing gear. There just isn't really a decent data set for that yet, although there are some good methodologies being developed for how to approximate that. We're not counting appliances, we're not counting finishes like paints and stains, we're not doing trim, we're not doing stairs, and we're not doing sort of driveways or porches or decks or anything outside the house. for lack of data and also for, less actionable analysis. If I tell you what the carbon footprint of all the drain pipe is in your house, it's a number, but you're not going to decide to not have drains because, you want to reduce that number. So right now, when you're seeing the results of these studies and from BEAM in general, it's this structure, enclosure, and partition materials. And so we have done a few studies of as-built homes, including the one that we did for Nelson and Castlegar, which looked at 34 as-built homes from 2020 in your region. We also did a large study for the Toronto region of 503 houses, and we just finished one for Vancouver, which used 13 as-built homes. And what we found was when you count those structure, partition, and enclosure materials, and you sort of use the methodology I've just described, at the high end, we get some pretty big numbers, including, an example in Toronto that was over half a ton, 561 kilograms of emission per square meter of heated floor area. So, if you think about half a ton of emissions for every square meter in a building, there's clearly, at any of these ranges from 300 to 500, there's no way we sort of hit climate goals if our buildings are responsible for emissions at that kind of level. Then when we averaged the results of all the buildings in each study, the averages sort of range from 150 to 194. Interestingly, the Toronto and the Vancouver numbers were very, very close to each other, despite there being a lot of design differences and climate zone differences and code requirement differences between the two. It was interesting that they aligned really closely. And then at the low end, we found some buildings that were surprisingly quite a bit lower than the average. Surprising, especially because these were just randomly selected homes. So nobody was setting out to make a low carbon building. They were just, this is capturing somebody's business as usual practice and seeing that there's quite a significant reduction to be made there. So if we kind of take that Toronto, Vancouver average of about 200 kilograms of emissions per square meter of heated floor area and multiply it by the amount of building that gets done in low-rise residential sector in Canada every year, we're kind of looking at about 12 million tons of emissions annually just from new homes in Canada. And that equates to the entire country emissions of some of the countries you see here, El Salvador, Jamaica, Luxembourg, or to put it in a different way, it's the equivalent of about 6 to 8 coal-fired power plants every year. So, if we can knock 30%, 40%, 50% off of our total for each house that we build in the country, we can collectively be doing the same as getting rid of 2, 3, 4 coal-fired power plants, which is a pretty significant impact to be able to have nationally.
Sorry, just a quick question. Just with calculating all of that stuff, are you looking when you look at even the comparisons of the different regions, are you looking at similar size buildings to come up with these numbers? Or because I would think that your embodied carbon would come out way different if you're looking at a small home versus a really large home. And then also when you say the difference in the emissions between say Canada and El Salvador and Jamaica, of course we're going to have a huge difference in the type of houses because they're hot climates, and we have to build totally different. So to me, it's kind of a moot point when you're looking at it from that side. Not that it doesn't matter, but we're gonna have a much different embodied carbon just based on our climate.
Yeah. Well, what I'm comparing it to here is not the emissions of their buildings, but the emissions of their entire country. Everything they do, all the transportation, all the the industry, everything that happens in Jamaica is almost the same emissions as just us making materials for new houses in Canada. So I guess I'm trying to give it the sense of our little sector of the industry in Canada has the same impact as if we showed up at COP, we would be like a country in terms of the amount of emissions that just our sector has. So hopefully that makes clear I'm not comparing it to their house, but to their entire emissions output. And then the reason that we express the answers in terms of square meters of heated space is to sort of equalize across house size. So that's, we could show the answers in terms of gross emissions for the whole house. And that's then harder to compare. If you say, well, this house has 12 tons and this house has 60 tons, if the house is 5 times bigger, then that makes sense. So we're expressing it in terms of, emissions per meter squared to, to sort of try to solve for that and make them more comparable.
Right, for sure. That makes sense.
Yeah. Okay, so, if that kind of sets the groundwork for, how we calculate it and sort of what we know about it, then we'll sort of look at, how we go about reducing these emissions. So I guess the first thing is that, some people have already done a great job of reducing these emissions and they don't even know it. So, in our Nelson and Castlegar study, there was a builder not setting out to make a low carbon house because, these were results that came from 2020. Nobody knew this study existed. Nobody was really thinking about embodied carbon. So somebody's business as usual is already 50% reduced from what the average in your area is. And similarly, in Toronto, that result of 116, that comes from a developer who makes, 200-300 houses a year, not setting out to make a low carbon house, just making material choices that, land them in that range. And then similarly in Vancouver, it wasn't quite as dramatic, but even there's a 30% reduction. So, what that sort of points out is that some pretty substantial gains are there to be had already. We don't need any sort of magic formula or secret sauce. We just need to know what are these builders doing that are already getting their houses down there, because they're doing it, code compliantly, affordably, practically, all of those sorts of things. So none of those issues are barriers in at least making this kind of substantial reduction. So we did a study for a developer here in Ontario called Doug Terry Homes. And they have already for about, I think the last 7 years, only been making net zero ready homes for, across their entire portfolio. So they felt like, well, we've done kind of everything we can do right now on the operational side for the climate. So what can we do on the material side? So they gave us the plans for a number of their model homes, and we kind of took them, a number of them. I'm just going to show you one here because the results were sort of the same across all of them. We took this one model and we modeled it out for them in a bunch of different ways. One interesting way is that we modeled it as though they were only meeting Ontario code minimum for energy efficiency instead of net zero, because they wanted to know, how much were they increasing their carbon footprint by going to net zero as opposed to just building at Ontario code minimum. And you can see it was a pretty substantial difference. 48 tons went up to 66 tons when you make the jump from code minimum here in Ontario to net zero. Then the next model we made for them was, well, in adding all that extra insulation between different manufacturers of the insulations you're already using, there's a pretty substantial carbon footprint difference. So without making any changes to your materials, just by selecting the manufacturers with the best carbon footprint, you could actually get your 66 tons down to 52 tons. So in other words, you could make a 20% reduction in the carbon footprint of the building without even a material change, just by looking in Beam and going, oh, manufacturer A of spray foam has a better carbon footprint than manufacturer B, and same with, all the different insulation products in the building. So, a really big impact can be had just by that kind of sourcing. And then the model that really, was surprising to their team was that when we looked at, well, what if we're willing to make some material substitutions, again, not changing the performance, not changing anything about the design of the house or the types of trades you would need, but just swapping out materials that were pretty easy to change out. We could get that carbon footprint down from their as-built. We could take 65% off of that with material substitutions that were both sort of practical and cost-effective and didn't, throw any hiccups into their process. And then we made a few other models where, the changes would be a little bit more dramatic and/or would require them to find different supply chains or trades or things like that. And then finally, a future scenario where, if we could apply all the materials that we know are the best for the climate, but that aren't currently, widely available or necessarily code compliant, we could get that house basically down to a net zero. So that was the sort of range of options we showed them.
Hey, Chris, on that, I think you're about to answer my question. Never mind.
Yeah. Yeah. So really, I mean, interestingly, that 65% reduction, one-to-one substitutions, there were really just these 5 things that we did. That plus, I think we also looked at changing the brand of drywall made a bit of a difference too. But really, the big impacts were changing their concrete mix. So this was not changing the amount of concrete, the strength of the concrete, where the concrete was coming from, or even the cost. This was just talking to their supplier about could they get, in Ontario's case, a high slag mix where you're sort of substituting a bunch of blast furnace slag for Portland cement. My guess is in BC that would more likely maybe be fly ash rather than slag, but there's a number of different waste products that can be put into concrete for the same price and the same performance of concrete, but a really dramatically reduced carbon footprint. We took the closed cell spray foam that they put underneath their basement slab and changed it out for an appropriate type of EPS foam board. We changed out their cavity insulation from their walls and their ceilings to cellulose. We replaced the carpet and hardwood floorings with cork and linoleum flooring, and we changed the brick cladding to an engineered wood cladding. And those 5 changes made up the bulk of that 65% reduction in the carbon footprint. And of all of these, only the cork and the linoleum flooring have a cost implication. In fact, the cost is either the same or less for the other substitutions. So, there's right now in the embodied carbon world, there's just a whole bunch of this kind of low-hanging fruit that we can move to, I think, pretty quickly and be seeing, in the range of sort of 50 to 65% reduction in the carbon footprint of the building.
Chris?
Yeah.
Question, with the concrete, is there any option for using recycled concrete for the aggregate in the concrete mix itself? Is that a thing that's considered? Because I know sometimes concrete, when it gets ripped out of buildings, ends up in landfill. And I have heard of people actually re-crushing the concrete to use that then as aggregate rather than using raw crushed rock for the aggregate.
Yeah, well, no, there's not a whole lot of that. And for a couple of reasons. One is it doesn't actually make that much difference to the carbon footprint. Almost all the carbon footprint of concrete comes from the making of Portland cement. So, crushing up a bunch of virgin rock and crushing up a bunch of used concrete, the energy use and therefore the emissions aren't that different. And sometimes the used aggregate can be more because you have to get the concrete, crush the concrete and move it to an appropriate place in smaller quantities than, just taking it all from one quarry. So I think, and also there's a performance difference between aggregate made from crushed concrete and sort of virgin aggregate. So I think it hasn't been used a lot because it's not necessarily cheaper, faster, or lower carbon. And so it hasn't really been a strategy that I've seen used very much.
Okay, thanks.
So one interesting thing that sort of came to our attention during the study that we were doing in Nelson was this house by Mike Cohen, where he was actually working to try to make a lower carbon house, both on the operating and the materials side. And it actually, he made a really great example of what's possible. So he got the operational emissions of the building were modeled to be about 0.14 tons per year, which was at the very low end of all the houses we looked at in the region. But he also got the material emissions down to a tenth of a ton, which again was a really outstanding result, and sort of points to the fact that not only can we reduce emissions by half fairly easily, but if you put your mind to it, you can get that down to pretty close to zero even today. So, this whole house, building it and operating it, is only going to produce 4.4 tons of emissions by 2050. So, as close to zero as you can sort of feasibly get, and it is a living example of some of the strategies that you would use to get there.
And I just want to add something, Chris, on that, just for you guys to note. In the Ontario case study, there isn't a cost difference for that increased slag mix, but for here, Nelson Ready Mix does charge a premium. So just so you guys know, the more that we ask of them, I think the less likely they're going to charge us a premium. So I'd encourage you to always ask, but I just wanted to let you folks know. And for Mike's case study, the cost was we're going to be coming up with a case study, so we'll have this data to present, but his project overall was not more expensive. But I just wanted to mention that.
Is it fly ash that they use here?
Yeah. Understanding.
Yeah, and the charge, fly ash is actually a lot cheaper than Portland cement, so it's not the material that costs. But if a batching plant isn't doing very much of that kind of mix, then the sort of you're paying for the pain in the butt of them having to change what silos they're using and how they're portioning out the materials. But I guess here in Ontario, mixing in the slag is a common enough thing that there isn't a charge for it anymore, because every mix is using it, even to some degree. 5 to 15% is kind of normal in a mix here. So then upping that, there's no difference for the batching plant other than to let a bit more of the slag in. But if you're typically not using any supplementary material, there may be a charge, like Natalie mentioned. So one of the things that I like to sort of talk to, especially when I'm talking to developers and builders about this, is, it's great to look at Mike's case study house and go, oh, wow, zero emissions, that's pretty great. But I think it's important to remember that, we have these regional and municipal and provincial and national targets for emission reductions. And, if I kind of take the kind of national approach here and say that we're trying to get, buildings like everything else reduced by 40% by 2030, then as a builder or a designer, you can plot this out. It's not like you have to start building that Mike Cohen house tomorrow. You can actually start to sort of approach this in a really planned out and rational way of, maybe in year one, you just do the concrete mix improvement. That's pretty straightforward. You can handle that. It's probably more than 5% reduction if you can do a high fly ash mix, but that would be a potential step one. Maybe in year two, you sub out one insulation, not for a different type, but just for the best in category. Then you can sub out drywall for best in category, etc. Whatever the steps are, whatever you think is most approachable and easiest for you to be able to do, this is something that you can actually plan out so that it's not highly disruptive to your practice, so that the changes aren't sort of overwhelming for the crew on the ground or procurement or anything like that. But those handful of steps staged out over the next 7 or 8 years gets you to that 40% reduction in a really feasible kind of way. And then obviously, beyond 2030, we can keep that, we can keep those steps going lower and lower. But I just like to sort of position this as something that's not necessarily a crazy radical change that we have to make overnight, that it's really approachable and feasible, and something that you can plan into your actual build cycle. So one of the questions that we set out to answer for the study in Nelson was, as you try to make the building more energy efficient, are you driving up the material emissions? And there's a certain way of thinking about that where you go, well, of course you are. If you add more insulation, if you add a third pane of glass to all the windows, if you all the things that you would do to make the building more energy efficient, add material, and therefore might drive up the material emissions. And so, is there a balance there? Are we going too far in terms of pursuing operational emissions and unintentionally driving the material emissions up? So when we looked at that study, so first we sort of looked at the operational footprint. So we had the models, the energy models for all of the buildings, and across the whole set, there was 34 homes. The average was just about 1.25 tons of operating emissions per year. And so, extended out for say 20 years, that's 54 tons of emissions over the next 20 years. But, that the overall footprint in 20 years, you don't really know until you know what these upfront emissions are, because that sort of like provides the starting place. The emissions of all the materials provide the starting place for where you start operating the building. And so, the whole point of the Nelson study was to see what happens when we add these two things together, and how big an impact is the materials versus the operation. And so what we found was the average across that study was about 28.8 tons. And this is where, to that question that came up earlier about different sizes of houses, this is now we're talking total emissions for the house. This isn't per square meter, but this is, if we added up the emissions of all the different size houses, 28.8 tons was the average for materials, and 1.25 tons per year was the average for operations. And so that meant that sort of on average, a building was having about 54 tons of emissions over the period of 20 years. So you can see that more than half of the first 20 years of the carbon footprint of the building is attributed to these emissions. So it takes 23 years before the operational emissions have equaled the initial impact of the materials. And that was the average, but the data was pretty well spread out. So we had a worst case scenario where both the material emissions were high, just up over 40 tons, and the operating emissions were high, getting close to 5 tons per year. So now that 20-year carbon footprint is 139 tons. So almost 3 times what the average was, and that's because both sides of the equation, the materials and the operations, were on the high end. And then we had a building that was at the exact opposite end of the spectrum, where its materials were really low, its operating emissions were really low, and so over 20 years, its carbon footprint, you could build and operate this building for less than the average home was taking just in its materials. So there's this wide range of potential results, even though all of these homes are in the same region, meeting code at least, and doing so in different ways. And so, looking at both sides of the equation, I don't know if this slide is particularly intuitive, but here we kind of arrange some of the results on the right in terms of if you add their material emissions and operating emissions together. We had 139 tons in 20 years at the high end. We had 17 tons down here at the low end, and a bunch, of possible arrangements in the middle. And so what I want to sort of point out is that, it's not an either or kind of scenario. You could, here, the second one is a house with very low material emissions, but if its operating emissions stay high, it's still the second worst case. So by only focusing on materials, you didn't solve the problem. And here we have one where the material emissions were really high, but their operating emissions down low. And that turned out to be a pretty good case scenario. And obviously, the best case scenario is where you do the best in both cases. But I think that the value of looking at the material emissions and the operating emissions is that you come up with strategies that get you the best result in terms of the overall carbon use intensity. It's not that we should pursue one metric or the other. It's that really the impact of the building is both of these things. And so how do you make decisions that do the best for both of these things? And you can get kind of granular about it. You can look at the building and say, well, what's the material difference in going from double pane windows to triple pane windows? And then what's the operational difference in doing that? And are the triple pane windows worth it? Or is the extra layer of insulation worth it? Or, you start to be able to analyze the building to get the best possible results. And one of the things that I think kind of answered Nelson's question in a really interesting way was that because we had buildings at all ranges of the step code, what we found was that they didn't, where they landed in terms of their energy efficiency wasn't really a determining factor of their material footprint. So, we had a couple step code 1 buildings, and one of them was among the highest carbon footprint, and one of them was among the lowest. So, that wasn't a determining factor. The top and bottom end of the material emissions range were both a pair of step 4 homes. So homes that were attempting to be, more energy efficient were both the highest carbon emitters from their materials, but also the lowest. So getting to step 4 wasn't, the thing that drove the emissions. It was the material choices. And then here in the middle, we have a couple step 5 homes. So kind of the best you can do on energy efficiency. And they both ended up in the middle. So it didn't, a step 5 home didn't have the highest carbon footprint. It also didn't have the lowest carbon footprint, but both of them came in at less than the average. So, I think what that means is you can pursue both energy efficiency and low material together. One doesn't necessarily drive the other in a bad direction, but they can. So hence, I think the importance of actually starting to measure the material side and making sure that we're not having that unintended consequence. So we kind of can apply the learning that you get from looking at the material emissions from using a tool like Beam at a bunch of different stages in the project. So that ranges from really early on, even thinking about decisions, whether to build or not to build, or where to build, or the size and shape and massing of the building, basic sort of assemblies that you're going to put into that building. You can model all of that out, pretty quickly and easily in a tool like Beam. And then, as you get into actually developing the design, you can start to really get into what materials and what assemblies you're using. And then during the actual construction, making sure that the procurement is matching what the model said, because even within, say a category like mineral wool bat insulation, the best performing mineral wool bat and the worst performing, there's almost a 3 times difference in the carbon footprint. So, if you're trying to do the low carbon build, your designer might have specified a certain mineral wool, but if the procurement doesn't follow through, then the results of the model aren't really going to be true. So it just becomes something I think that designers really build into their considerations, and can kind of like use that to make decisions along the way. And my own dive into embodied carbon came from the fact that in our design build practice, we were already trying to use metrics in all kinds of different categories to help shape our decisions. So we were, measuring ecosystem impacts. We were measuring energy efficiency. We were measuring, indoor environment quality. We're measuring waste, all of these different things. And so embodied carbon, I think, should not be, the one and only thing that we use to make decisions. You don't always necessarily want to or need to choose the lowest emitting material in the category, because we're trying to balance all of these factors. We're trying to balance cost and code compliance and durability and efficiency and environment quality and all of these things. But now that we can actually measure embodied carbon, it becomes one of the pieces of information that we throw into the mix when we're trying to figure out a building. And we're constantly making trade-offs in all of these areas with each other. You could just pursue the absolute most energy efficient building in the world, but it might end up costing you a bunch more. So you scale back slightly. You aim for step 4 instead of step 5, or whatever the decisions happen to be. I think embodied carbon sort of needs to take its place in those decisions, but it's not, it shouldn't be the sort of the guiding principle, but it becomes one of the things that we study. So that's the end of the presentation portion. There is a bunch of different reports if you want to dive into this a bit more, including the one from Nelson and Castlegar, but also the one that we did for NRCan for the City of Toronto, and the report from Vancouver literally is just getting posted on our website today. So it's kind of, as Natalie put in there, hot off the press. And you can sort of read more and in more detail about all of those things. And just want to thank the City of Nelson and FortisBC for their support of the research and of these sessions.